My name is Sri Reddy, and this is my lab on oscillations. So, the purpose of this lab was to computationally analyze the motion of a hanging spring mass system. We do this because it physically models a stretchable rope, which has many applications in real world, like as you can see in the picture, bungee jumping. We'll be analyzing the phenomenon using two fundamental principles. First, through a free body force analysis in a free body diagram that allows us to see Newton's second laws that update the position and velocity of our mass. The two dominant forces acting on this mass is the force of gravity and the force of the spring, which act as a sum together to form F net. We can also analyze this system from an energy perspective, where we can consider both kinetic, gravitation, as well as spring potential energies of the mass. The formulas for each of these energies are shown below, and we can describe the system through these various formulas. As a basic result, we should see the x and y positions of the mass change in a wave pattern. And we should also see the energies of the mass change relative to the position in y and along the spring axis. If, for example, the spring is compressed, there will be a high spring potential, and if the mass is high on the y-axis, there will be more gravitational potential energy, and we can observe this shift throughout as the mass moves along the spring. As you can see here, this is our experimental setup, which consists of a spring and a mass, which bounces up and down, and goes left and right along the board. And we use this to model the potential energies of like the kinetic spring and gravitational potential energy. And in order to solve the initial conditions for the system, we need to estimate the period of mass using the data in the experimental setup. Then we use this value t to calculate the spring constant, which can be used to calculate the relaxed length of the spring. We can input this data into code as initial conditions for our computational study. And we put this through a calculation loop where we are conducting our second law analysis and calculate the individual forces, then Fnet, acting on our system. We then use these forces to calculate our change in velocity and position for our delta t. We follow the calculation with our energy analysis, and we can directly apply our energy principle equations to calculate our change in energies for this delta t. And as you can see, these are results for the position data. And while the x is more closely aligned, the y is a bit wonky. It's not as closely aligned, but it somewhat models the behavior of the experiment. And but we could say that we are still predicting the movement through our experimental model. We also discussed any potential errors that may have caused this movement, as we will see soon. And also here is our energy results. As we can see, delta E stays constant throughout because energy does not is like not destroyed or anything like that. It stays constant. And as you can see, the delta K fluctuating gravity as well as U grav in respect to each other, which 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 like cancels out each other in the end to form the delta E, which is zero. And that's what we see from this computational model. The possible errors that we could see here are tracking errors. There's obviously going to be maybe some tracking errors that we might have seen on our analysis on tracker, and that could have made some errors as well as some computational assumptions that may have thrown us off a bit. However, since we made our delta 2 quite small, we can safely assume that most of our errors are from tracking software analysis. So, what does this mean? This means the energy principle is not completely satisfied because we do not account for the change in kinetic and potential energy of the Earth. These values are so insignificant, however, that in essence our principle is complete. The average periods that I calculated for these values are shown above and are quite similar. However, I did see that Y calculation was more precise with fewer variations in each period measurement. Sorry, X. My X calculation was more precise. And yeah, that is all. Thank you for listening.